everybody. This week we shall look at the relevance of the matrix calculus in plane geometry. That will be the main part of this week, and then we come back to the language of mathematics. So let me start with the plane geometry. So what do I mean by that? So imagine you've got a plane, something like this. So imagine the surface of your desk, right? And you want to forget about what are the scales there. You don't have any system of coordinates, so you can't say that a point in the plane would be the same thing as a couple of numbers. But if you want to, you can make it to be, right? And you do it in such a way that you simply choose one other point and then yet another point here. And these will be two vectors. Let me call them E1 and E2. So just any couple of points in the plane gives me the vector, which is something like move in the plane, which will move the point to the other one, right? So that's the way how I want to see it. And then of course, once I got this, I will get the corresponding, say, system of lines in the plane, and the other ones will go this way. And this you can see as a grid. So if you would be interested only in some of the points, say what we would say integer coordinates, right? Once we've got the coordinates, then you of course can say how many times I take this one. So this vector E2 will be taken, say, this many times, and the vector E1 minus this many times. And this will correspond to the point which is somewhere here. Right? So you see that instead of having plane as such, I can just associate it with couples of points. But that's when I fix my so-called origin, and I fix the two vectors which I take as most important. So this one, and this is what we call a base. Right, so that's roughly what we try to introduce in the beginning, and we know that the vectors can be combined in such a way as I just indicated when talking about the coordinates. And so whenever I've got one of those vectors, like say this one and this one, so I can just add them together and get this one, right? And this is not just adding them together, but I was taking 2 times of the vector u and v and w, because this one was w and u and v, and this one was just v, right? And this is just u plus v. So you can see on the figure what I mean by adding the vectors. That's very easy. And there is not much more, because then the points in the plane, as we see them here, they are nothing but couples of real numbers, right? If we take the real plane and then we fix the vectors E1 and E2, right? So I just fix the vectors E1 and E2 here, and that changed the surface of my desk into something like a grid, and I can read off the coordinates of any point there. And that's exactly what's happening. And the adding of vectors is then nothing but adding the coordinates, right? Because from the very definition it works like that. So I simply get addition of points. So I have something like a point. You will see in a moment why I am writing it into columns. So I have a point, say x and y. So that will be a point, so it's in the plane. And I add some v and w. That's the vector, so it's a point and a vector. And the result will be just the point I am coming to. And that's nothing but the sum, x plus v, y plus w. But it's important to see that this is a position, while this guy is a change of the position. That's two different things, right? So conceptually it's different. And this way we can define then the basic object in what we call an affine plane. And in the affine plane we do not have this origin, which is called usually, well, anyway, but I will call it O, which is the same as a 0. So this is something like fixing the point P there, fixing the origin, and then when I fix any point, it's given by the same as adding the appropriate vector. And things like a line are then given in an easy way, because I fix the point, which is a point on the line first, and I fix the direction vector, and then I parameterize it with the real parameters. So I add all the multiples of the one vector, right? So if it was here, so I would just have the point P0 here, I would have the V, and then I would have the entire line here through, because that's obtained by adding all the multiples of V to the single point P0. Of course, if I start with another point, then I can do the same, except the parametrization will be different, right? If I imagine it as a straight movement through the plane, then what it means, I'm just making a shift in the time, parameterizing the movement. So it's nothing but that, so it's all very easy. And it's not difficult to see that a line in a plane is given exactly by a implicit equation as well, because of course, I mean that's how it is. So if I would just write it as a so let me move it this way. So if P0 was x0, y0, and I've got this vector V, which is something like, well, V1 and V2 say, so it's not very consistent, but you will understand. Then of course the general point P on the line is equal to x0, y0, so I write both the coordinates at the same time, plus t times v1, v2. So if I write this one as xy, then I simply get the equations. X equals x0 plus t times v1, y equals y0 plus t times v2. And you know that this, and this are fixed scalars. So we can eliminate the t. So t will be eliminated from here and here. And what I get is exactly this kind of equation, right? So that's very easy. And you can imagine that if you want to describe implicitly this way a point, so it's possibly described in really many ways as an intersection of two lines. So you can write the first line, the second line. And now we come to the good point, because how does it work here? So it's this way. Because you can also imagine the things in such a way that you will have the plane once here and another copy here, and I will just write down something like a mapping, which is just exactly the mapping which you see on the other side, right? So I take the vector x and y and I map it into Rs. And the formula for this mapping is on the right hand side, a very simple one. And that's what we call a linear mapping, right? So it's linear because I can write it in a very special way, and also I know that if I work with adding the vectors, so this very mapping will be the only way how to get a mapping which preserves the linear combinations of the vectors, right? So that's very important, and that's here. So this is the prescription of what is linear mappings, and immediately if it should preserve the linear combination, then of course if we just jump back here to the very first thing, so here, so then you may imagine, if I know value of such a mapping on the vectors E1 and E2, of course 0 must go to 0, so the origin has to go to origin, right? And if I prescribe the mapping on E1 and E2, then because every other point is obtained by linear combination, I know it everywhere. And if I want to get it as a nice computational tool, then what I can use is what the people call matrices, and that's exactly what's happening here, right? So here I write the matrix A, where the values on the first vector and the second vector would be given by in the first column, and those on the second vector are in the second column, and that's exactly what I get. And you see that if I multiply the thing as I want it, then I get exactly the prescription I was after. So this is the thing, and this gives us the understanding of what the people call a matrix calculus, because actually what you see is that what I'm getting here is I take the first line, the first line only, and doesn't want me. So the A is multiplied by X, and the B is multiplied by Y, right? So I multiply this way, and A times X, B times Y. And if I have more columns, I can do it with the second column as well. So if I would multiply a matrix, I call this matrix, with another matrix, then I get again a matrix, right? And this is called scalar product. And it's very easy to see that actually if I restrict myself to matrices of our kind, so I have got only a line, that's a matrix for me. I've got just a single scalar, that's a matrix 1 by 1, but that's not very interesting. And I've got individual columns, and I've got the squares, the 2 by 2 square matrices, right? And whenever it makes sense to make the multiplication, which happens always if the number of columns of the left-hand matrix is the same as number of rows in the right-hand matrix, then I can multiply them. And you see immediately that the multiplication is associative, the distributivity law works both ways. So in some sense the matrices, in particular if I restrict ourselves to the square ones, they behave very similar as our scalars. Nearly everything works, except the multiplication is no more commutative. And here is an example, right? So that's a very straightforward thing. And this is the basics why the matrix calculus is so useful and everywhere present, because it's exactly what we need when we want to talk about the linear mappings or the linear mappings with some constant shifts, edit, and whenever you want to work with computer graphics, with data, in statistics, in data analysis, you will find it everywhere. There will be matrices appearing. And there are special things to tell about the matrices, and one of them in our case is what we call determinant, and that comes from the request to have something which would tell us whether such an equation has got a solution and a single solution or not. So that corresponds to the fact that two lines given by these choices of A, B and C, D have an intersection, and you can imagine that mostly they do. But there are situations where the lines are either parallel, then they have no intersection, or they coincide and then they are the intersection themselves, right? And that's all told by the determinant. So you can see that the two lines, if they are two rows in this matrix, if they are a scalar multiple, so the second vector would be just a rescaled first one, then we have to see that R and S are in the same ratio. And if not, then it's too parallel lines which are different and there is no intersection, and if yes, then it's just all of the lines are the solution. And you see that to be one multiple of the other is equivalent to this equation 1, and that's called the determinant. Right, so that's nice because we've got a nice scalar invariant which is computable and which tells us whether the matrix is having the property that the relevant system of equations will always have just one solution for each right hand side. And as I told, so we are interested in also adding a shift. So if I have a matrix which gives me a linear mapping and a constant vector w which makes the shift, then in total the mapping sending x and y as a general point in my plane to this thing is called an affine mapping. And this corresponds to a very important thing because it tells us how it is with the coordinates I started with, right? Remember, I started with the coordinates, so in order to get coordinates we had to choose the origin, and we had to choose the basics, the basic two vectors. And imagine that there are two people and each of them has got their own origin where they are, or they know they will be soon, and the two directions of their basic understanding of what the plane is would be different. So if the girl just says let's meet at the point 2, 1, of course for the boy it's not that easy to see which point in the plane it is, but if he knows about his O and her O dash and his E's and his dashed E's, then he can very easily compute what would be the relevant mapping which transforms his coordinates into hers, and that's what's also given by the matrix calculus. So I think that's enough for the, say, guidelines, and I hope you will look at, well, either you find it trivial and you know everything already and you are looking forward to get it further, or you will read through carefully and you will find out that it's really easy, and later we shall see how much useful it is. So thanks for your attention.